In section 5.4, we will explore exponential and logarithmic equations. First, we'll revisit the principle of logarithmic equality, which we saw in the previous section, which states that two expressions are equal if and only if the logarithms of those expressions are also equal. In other words, if two logarithms are equal and they have equal bases, then their arguments must be equal. Next, let's look at a four-step process for solving equations that are written in exponential form, such as a to the t power equals b, and we're trying to solve for t, the exponent. The first step is to take the logarithm of both sides of the equation. Now you can take the logarithm of any base you choose, but because our calculators come pre-programmed with base 10 and base e, the common and natural logarithms, either of these two would be a wise choice. Second step is to use the power rule for exponents so that we can release the variable from the exponent and bring it down as a coefficient. Third, we'll divide both sides by the coefficient of the variable to isolate the variable. In some problems that are a little bit more complicated, we may have to do additional steps to isolate the variable. And then finally, if appropriate, use a calculator to find an approximate solution in decimal form. Now, I want to make a note that in some advanced math courses, it is going to be preferred that answers be left in exact form. So I'll make that distinction as we work through the following examples. In our first example, we have 4 to the x power equals 5. So in other words, what exponent must be placed on a base of 4 to get the result 5? I'm going to take the natural logarithm of both sides of the equation. So we have natural logarithm of 4 to the x power equals natural logarithm of 5. Now using the power rule that we saw in the previous section, I can bring that exponent x down as a coefficient of the logarithm. So I can write the left-hand side as x times the natural logarithm of 4, and the right-hand side stays the same. Notice that in order to isolate the x variable, all that would need to happen is division by the natural logarithm of 4 on both sides. So finally, we get that x is equal to the natural logarithm of 5 divided by the natural logarithm of 4. This is what we mean by an exact answer. It cannot be simplified any further, and this is an exact value. However, if we are asked to approximate this value, we can use our scientific calculators to do so. I've worked this out previously on the side, and I have found that the natural logarithm of 5 divided by the natural logarithm of 4 is approximately 1.16096. You may want to pause the video and practice using the calculator yourself to see if you obtain a similar result. There's no hard fast rule as to how many decimal places you have to keep in your answers, but for the purposes of the examples in these lecture notes, I'm going to take my solutions out to 5 decimal places. Now, to me, it's always important that students understand what their mechanical work represents. In other words, what is this all for? The original question was, what exponent must we place on a base of 4 in order to get the result 5? So to check if our solution makes sense, we can raise 4 to the 1.16096 power on our calculators, and we'll find that that is indeed approximately 5. In fact, when I did this on my calculator, I got 4.9999 out to several decimal places before encountering another digit. In example 2, we have 6 to the x over 5 power is equal to 5. Similar to what we did in the previous example, we can take the logarithm of both sides. This time, just to show you that using a different base also works, I'm going to use the common logarithm, which is the logarithm base 10. So we have common logarithm of 6 to the x over 5 power equals common logarithm of 5. Once again, we'll use the power rule to release the exponent in the argument and make it a coefficient of the logarithm. So we have x divided by 5 times logarithm of 6 equals common logarithm of 5. Now I can start isolating the x variable, and I can do it in one step by multiplying both sides by 5 to clear the denominator on the left, and then dividing both sides by the common logarithm of 6. So for the sake of space, I'm going to do that all in one step, and I'm going to have that x is equal to logarithm of 5, or I should say common logarithm of 5, times 5, divided by the common logarithm of 6. Again, this is an exact answer. So any of you who are asked for exact answers in the future, this is what they're asking for. However, if I want to approximate this answer, I get approximately 4.49122. So if I check this approximate answer, I should be able to verify that 6 raised to the power 4.49122 divided by 5 is about equal to 5. And again, you can pause the video and take a moment to practice with your calculator to see that this is indeed the case. So I want to, again, make the distinction between exact answers and approximate answers. So exact answers do not require a calculator. Approximate answers now have some rounding errors. Shouldn't have said answers plural, just answer singular, but that's okay. Let me see if it'll let me erase the S there. Good. All right, very well. Let's take a look at some additional examples. Next, we have 5 raised to the x plus 4 power is equal to negative 32. Now, I already sense that we're going to have an issue here, because 5 raised to any power, whether it's a positive power or a negative power or even to the 0 power, should result in a positive result. But let's go ahead and show why I have this bad feeling here. If we take the natural logarithm of both sides, now I think the problem is clear. On the right-hand side, we have the natural logarithm of negative 32. And you might recall from earlier discussions that arguments must be greater than 0. So this tells me that this equation will have no solution. In the next example, I'm going to go and use the common logarithm again, taking the common logarithm of both sides. And this time, I can bring 2 different exponents out front to become coefficients. Now, these exponents are binomials, so when I bring them out front, I want to make sure that I enclose them in parentheses for clarity. So we have 4x minus 2, all multiplied by common logarithm of 15, equals the quantity x minus 3, all multiplied by the common logarithm of 4. Now this problem is going to take me more space than what is allotted, so I'm going to make some space temporarily by whiting out the example below. We'll recover it in the next video. So because I'm trying to isolate the x variable, and the x variable appears in multiple places, I'm going to distribute on both sides of the equation. So we have 4 times x times the common logarithm of 15 minus 2 times the common logarithm of 15 is equal to x times the common logarithm of 4 minus 3 times the common logarithm of 4. I'm going to underline everywhere that I see x, Now x is a coefficient, and I can combine like terms as long as I get those terms on the same side of the equation. So in the next step, I'm going to bring this term over to the left, and I'm going to bring this term over to the right so that the x terms are on the left and anything that does not contain the x variable is on the right. So remember, moving involves adding and subtracting. So I have 4x common logarithm of 15 minus x common logarithm of 4 is equal to 2 common logarithm of 15 minus 3 common logarithm of 4. Now the two terms that contain the x variable are together on the same side, and I can factor out x as the greatest common factor. So in the next step, I'm going to have x times 4 log 15 minus log 4 equals, and then the right-hand side stays the same. So we have one more step to isolate the x variable. We would need to divide both sides by this binomial that x is currently being multiplied by. So for the final exact answer, we'll have x equals, the right-hand side stays the same, and in the denominator, we'll have 4 log 15 minus log 4. So again, this is an exact answer. However, if you want to approximate this answer, you will need to use your calculator very, very carefully. So I have not worked this out previously, so let's take a moment together to use our calculators and solve for this approximation. And I'm using my smartphone calculator at the moment. So even the one on your smartphone, if you tilt your screen sideways, will give you what you need. I'm going to write some intermediate steps here. And I always get a little nervous when I have a lot of things to type, but writing down all your steps and then using what you think is a solution to substitute back in to just check to see if it makes sense, that's what I would suggest you do.